I've been, this morning was like, this movie Sophie's Choice, where you have to choose, which of your children are going to live and which not, because I had to choose what topics, it's just one lecture. Before, when you have more than one instance of infinity, and you will be able to say everything you want, but now, I have to cut things off. But we were talking about, what is learning and, what is research. I really like this quote from Thurston. It's in some post he made in Math Overflow. There's more interesting stuff. I just pick a little bits and pieces that for me they are the highlights. And just wanted to emphasize, the point is really understanding. We really have to understand something very well. That's what we're doing. And of course, it's easy to say right now, after a long and winding road, I have tenure, so I know that papers are important and everything, but, there's these two paths, we want to do as mathematicians, and then, the real life that also you have to deal with. Okay, so let me stop the blah, blah. I'm going to explain, hopefully not too quickly, how to, I've been trying to talk about how I put the math I'm thinking about in the computer, and then, run experiments to make conjectures and then prove those conjectures. So this is a super fast way of how, super fast overview of how can we measure length. So remember that we had a surface with a hyperbolic metric, and we said when you have a surface, every deformation classes of curve has a unique shortest curve in that class on this surface with a fixed way of measuring length. That's called the geodesic. So how do we input those data in the computer, and how do we find these metrics? So here is a nice way of doing it for the pair of pans. You heard, somebody said that, I think yesterday, maybe Amy, that it was also Sarah, well, one way to do it is you start making pairs of pans. I said yesterday, if you remember, the pair of pans is this sphere with 3 holes, and the length of the 3 holes determine the whole metric. So you can have, and it can be any positive, triple of positive real numbers. So then you can, if you have pairs of pans, you can glue them together by the cuffs and make a surface. And there's also one twisting, but let's not worry too much. So thing that you can attach, and of course, if you glue 2 cuffs, they have to have the same length. In the cuff, these are also they are geodesics. So let's see how to make pair of pans using matrix. So this is the upper half plane, and the green and the blue are 2 geodesics. So we are given 3 numbers. They are A, B, and C. I didn't write it down, but this is 1. This is A. It's a number between 0 and 1. B is a number larger than 1, and C is a number larger than B. I have these 3 numbers. Then I'm going to draw the geodesics, which, well, you have to trust me, we didn't explain it a lot, but these are half circles perpendicular to the boundary of the space. Sometimes you will hear about, and I mentioned it today, the boundary of the upper half plane is not part of the structure. Our space is really R2, locally. Our space has no boundary. The points in the boundary are not points in the space, but we can see them from our space. They form part of the structure. So they have, they say things about our space. So for instance, the endpoints are significative. Oh, here it is. Yeah, I said that, So I start with the 3 real numbers with those conditions, and I'm going to get 3 maps. Here is 1. This is just the reflection, the standard reflection across the y-axis. The other map will be a reflection. Now remember, this is a hyperbolic line here. This is also a hyperbolic line. And this map with this formula is a reflection, is a hyperbolic reflection. So this is like a hyperbolic mirror, so you have to think the equivalent or Euclidean if you're not familiar. And this is, has this nice formula. And finally, we have the reflection about this other line. This is all in terms of, as you see, these real numbers A, B, and C. Now, when we have one of the nice features of the hyperbolic plane is that, well, let me discard that sentence, the beginning of the sentence. We're going to look at a group, which is, let's compose these things in pairs. So let's compose this with this, give a certain transformation. These are isometries of the hyperbolic plane, some isometries that I choose, and you'll see why in a second, hopefully. And the composition of this and this. And then, these are two isometries. I take all the possible compositions of these elements at the end, just get a group. And then I'm going to say, OK, let's take the hyperbolic plane and quotient by the action of these groups. Again, two elements are equivalent if one is the image of the other by an element of this group. So here I put the little matrices, and I'm not going to explain it. And if somebody's curious, I'm not saying it all because of sake of time. But these are, the matrices are basically, here, these coordinates. Well, I have these zeta conjugates. So these are the compositions, but let me skip. So what do I get? Well, this is amplify that picture. These two lines, the green and the purple, have a unique common perpendicular. This is another feature of the hyperbolic plane. This is here. This green thing will be one of this piece will be glued together. I have this isometry now, and this will be a piece of a cuff, and this will be another piece of a cuff. So what I'm doing to make me a pair of pants, maybe I should show you the pants here. These isometries are going to glue this blue segment with this blue segment, this green with this green, and those are the cuffs. And then the purple, the purple, notice that it goes from the pink to the orange. It goes here. Should have drawn it. So I'm gluing this. You have to look at this shape here. I'm following. It's an octagon with right angles. When I glue two pieces with right angles together, I get a plane. So here, these are the two right angles I'm gluing, and I get a nice curve that is a geodesic. If you don't have right angles, you might glue in an angle that will not give you something straight. So it turns out that the length, I think I wrote it down, the length of the cuffs, the length of each of the cuff, you can obtain it. Each of the cuffs is assigned by one of the transformations in this group. For instance, the cuff corresponding to the perpendicular of purple and green is the one that is the composition of purple and green here. That's a matrix. That matrix has a special line, which is this green line, is the common perpendicular of these two, and that line has a property that when I apply to each of the elements here, the matrix, I stay in the line, not point-wise, but the line goes to itself. This point goes to this point, and the trace of the matrix is related to the length of the cuff. Sorry, I was pointing this, which is not a cuff, that's a seam. So we should go here. So the trace of the matrix, with these two elements, the green and the purple, is related to the length of the cuff with that formula there. But it's nicer than that. So this is like the element, one of the generators that I called A yesterday. One of these, that were making the cuts. So now that we can find the length. Sorry, I'm going to say like the length of each element, each word. Now remember that we had these words of A's, B's, and A minus 1, A minus 1. I want to find the length of the geodesic in the class labeled by that word. So the way to do it is you're going to replace each letter by the corresponding matrix. One of the matrix for A, the other is the matrix for B. And of course, if you have the matrix for A, the matrix of A minus 1 is the the inverse of that matrix, or you replace the matrix, you get a new matrix. The trace of that matrix is related with the formula of the cosh to the length. Sorry, this was maybe a bit too fast, but that's a way, this is something that you can input in a computer. So then we have three numbers. We have a curved word, we have a surface width boundary, and we have different ways to see it. It's a deformation class, it's a geodesic, you can also identify with a geodesic, it's a conjugacy class of the fundamental group. And there's three numbers we can associate. One is the self-intersection number. This is just associated to the deformation class. One is the word length. This word length is not, independent. It depends on how do I cut my surface. So always I fix a priori how do I cut my surface. And then we have the geometric length, and there you need a choice of a hyperbolic metric. But if you make these two choices, you have these three numbers. And now, we can study relations between the three numbers. So here I have relations between two. This is another picture I really like. This is a flipped of the one we discussed. This is here now this is word length, the x-axis, and here is self-intersection. So in each column I have all the words of a fixed word length. If it's black, this means there's no curves in that box. If suppose that we are looking at here the word length 15, the darker the color is, the more elements I have. So this picture says here is well I have the most. This picture shows again that Gaussian I discussed yesterday, where in the middle we have the most amount of curves. Word length 21, and the self-intersection is more or less here. This will be the average of that Gaussian around here. Like say 50 something. And then you have less and less and less when you go to the edges. This picture here is the same picture, or the analogous picture, but now with hyperbolic length. So now I have here, of course, hyperbolic length, these are real numbers, so I cannot put it in boxes. So what I said is, okay, let's put just a little box whether you have curves between length of, say, 1 and 2 and a given self-intersection. So I just divide this in boxes, and I count all the curves in one box. And notice the similarities of that pictures. Really the combinatorial world is kind of an interesting mirror of the geometric world. Here you see this quadratic function. Somebody mentioned this Basmagian result that you have. Well, we can say that, how can we bound? If we know that you have a certain word length, your intersection is bounded here. You can, by this quadratic function. No, not word length. This is, sorry, it has a geometric length. What else do you see? Anybody can tell me any pattern? Yeah, that is there. I don't have still an explanation, so this is a theorem waiting for you. Yeah, there are these patterns, that I don't know. I don't have a way. One day I would like to, we should meet again and have a complete description of this graph, which explains really geometric length and self-intersection.
Well, the scallop seems to be quite regular. So
yeah.
The sort of length. So does that have some geometric meaning in terms of the metric? Sort of like the minimal length of a geodesic or something. I have no idea. But
this is, as I said, this is a particular metric. By the way, I choose a particular metric to do this. All the tables give the same. I couldn't find anything. I did some trials. When you experiment with geometric lengths, I have limits with what I can do because of, sometimes, I cannot take, when I experiment, I have to make sure that I do all the geodesics up to a certain geometric length. Now, if you have to do all the words up to a certain word length, you close your eye for a second and you see you can do it. That's not a hard thing to do from the computer point of view. All the words we can construct in our mind right now. Now, all the geodesics, it takes a little more work. You have to use some inequality and stuff, and then you have usually all the geodesics, they are less. So my experiments are limited. And the metrics I can work are limited too. So I don't know exactly, but maybe one day we can do something about this. Okay, so now the counting. Federica mentioned yesterday the counting of all geodesics up to a certain length in a closed surface. In a closed surface, we said they are e to the L divided by L. This is how they grow up, e to the L divided by L. This h that I wrote here is 1. Now, if you want to study a surface with boundary, they are, what do you think, they are less or more? It's, again, hard to say, but imagine this. Imagine you have a pair of pants. A pair of pants with very, very, very big cuffs will look like this. So if you want to have a lot of geodesics up to a certain length, well, you can see that you're going to cover a lot of lengths very easily. So if you give me a length that is not too big, there's not going to be a lot of geodesics. Because when you go around and do any curve that is slightly interesting, you are using a lot of your length. So this will give something that grows slower, So you need here a smaller h. And in general, there's a certain Cantor set. When you have this is a picture again, that the pair of pants that we obtain it by gluing this edge with this little piece is the boundary component, blue with blue, and I could continue. Now remember when we talk about this unrolling, we can unroll this pair of pants, and the geodesics, the closed geodesic, for instance, well, they are not going to enter here. This is a piece of a boundary. So when I look at a geodesic, this piece will not be used. It cannot go there. If I unroll it, we have to go over here. But then there's going to be another line here that is out. So all these chunks are going to be removed. And closed geodesics, when I unroll it, they will not allow to end here. So when I remove stuff, I'm going to be left with a Cantor set. The dimension of that Cantor set, the Hausdorff dimension, is this h. And let me not explain Hausdorff dimension, but we can talk about it in lunch. So this is it. Now here is, yes?
Is that the Hausdorff dimension within a concrete disk, or is it
within what?
Space? Is that within hyperbolic space?
Good, great question. No. It's now you look at the Cantor set is in the boundary, which is, here is another example where the hyperbolic space sees the boundary, but they are not pointing the space. Great question. So I like to visualize things. This is one of the things that are important for me for understanding. So I just counted all geodesics. So here, this picture corresponds. This is a torus, a certain torus with a certain metric, with a geodesic boundary component. I don't know if you can see these red points are counting how many geodesics we have up to, say, length 50. So here, this red dot says, I have, about 80,000. Up to length, 59, we have 300,000. So each red dot is that. The blue is an exponential function that I approximated to understanding, So I kind of estimated, using the red dots, I estimated the h just to visualize it. So this is the growth of all geodesics in a particular torus. This is like an illustration of this result. And this is the same with a pair of pants, with a particular pair of pants. Okay, and let me just. Okay. Now let's fixed self-intersection and counts all geodesics up to a certain length with a given self-intersection number. So, this is the result we already have. So a few years ago, there was this, somebody came and said, oh, you know what, there's this young woman who proved, like finally we know how the simple geodesics grow up to length, it's polynomial, and she has this amazing proof where she explains also conservative results. It was so, I don't know, I remember the emotion to see that. And of course I was, have the happiness that it was a, young woman doing that. So here is, a piece of, her result that was mentioned a few times, that if you look at all geodesics, I'm just using my notation, but this is, geodesics, with no self-intersection up to length L, the growth is like a constant depending on the metric times to the length to some power. That depends on the genus and the number of boundary components. It's polynomial. And we know the degree of the polynomial. In fact, she can even, and maybe I have time to discuss, she can even more or less say what is the leading coefficient of that polynomial. So, so this is just to insist on how non-simple simple curves can be. And later, very soon later, Igor Rybin, using her results, proved that the geodesic with self-intersection 1 have the same type of growth. And then, this is Vivica. This is last year, no? Vivica and Soto and Misakari also show that this happens if you fix self-intersection, you have the same type of growth. These constants, notice there's a little k there. So for each self-intersection, you have a different constant. Again, if we're all the same, and it would be hard to get this exponential adding all these same constants. So the constant depends on the metric and the self-intersection number. And this is, let me skip because I think I'll mention this later. So again, let me make a picture of all this result about growth of simple curves. Here I have again this is, let me see which is which. Gosh, I should have written. I thought, we have to. One is the pair of pans and the other one is. Oh no. These are torus. No, sorry. Sorry. I have to stop and think. This is a torus. Remember that I mentioned, one of the previous days, that the pair of pans is very special in the sense that it has finally many curves of a given self-intersection for each self-intersection number. In fact, one other thing that we don't know, so the number is, you have 3 simple ones, 3 with self-intersection 1, I'm not counting orientation, 9 self-intersection 2, and then there's a sequence, so how many you have self-intersection? 1, 2, 3, 4 in the pair of pans. That's a sequence of positive integers, is increasing, and I would pay to know how to generate that sequence. I mean, I can compute up to 20 terms, but I don't really, and I tried, and I look at the encyclopedia of integer something, and I think I asked QCAM, and we tried and we did stuff. It grows exponentially, and that's all we can say. Another thing we have to make another conference. And so this is just, again, red points are how many simple geodesics we have up to this length. So here in 120, I have how many geodesics I have in this metric up to length 120. The numbers are much smaller, of course. Here is, I have about 40 here. But notice how interesting that, again, now there are very few because, these are growing polynomially. I don't have a lot. My largest number here is 240. It follows a quadratic polynomial really fast. Again, the result is asymptotic. But look at here, I have, this is data coming out of the computer. I swear I'm not lying. You know, it's, these are two different metrics, and I put a blue polynomial to see. And I'm going to skip the other side. Oh no, this is, sorry, I invented, this is self-intersection 0 and self-intersection 1. Yeah, both have been the same. And so here I'm repeating the result I said before, a little more to explain. So this says that if I look at all geodesics up to a certain length, I fix self-intersection. Now this constant that depends on the metric that will show up in all, computation for all self-intersection. There's a rational number here, and this number we know what it is. It's pi, some power of pi times a certain rational, and we can say more about the rational in a second. Now this one is the pi square that appeared. Remember when we were counting curves in the torus, which is related to the number of relatively prime things, elements that add up to L. So let's see. And this is one more. Oh, sorry, this is the wrong order. One more picture of now same thing, but I'm counting self-intersection K, and well, this picture is a little bit different. I'm looking at the thing in a different way, which is here. My points are, this is some order. So I'm going to grab all my geodesics and put them in order, from smallest to the largest. And then I said, OK, let's look at the length of the first one, the length of the second one, the length of the third one. This is the sequence I'm trying to study. So here, for instance, this is the length of the 50th is around here, which is 20. So this is point of the form K, and the length of the kth geodesic. It's like the inverse of the function that tells me the growth. And again, well, this is now a square root. It has a minimum because, in these hyperbolic surfaces, we have a shortest curve of self-intersection K. So this cannot start at 0. It starts here. And the fact that this looks so flat, it's a little misguided. I put it just to put everything, but well, there are very, very few curves here. So in fact, this is showing all the geodesic up to a certain length. But if you put the bound on the length, and you said, OK, your self-intersection is really large for that length, you're going to have only a few geodesics whose length is really, really, really close. So this is what this is saying here. There's very few geodesics, about less and less, comparatively to the numbers that are here, and the lengths of all are close because, again, if I say self-intersection is large, you need, you don't have many options to have a bounded length. Let me see. I think I need to skip a little. I have to talk about. I promised Natalie Vala will talk about the Goldman Bracket, so I have to keep my promise. So now let's go back to Federica's talk, and she was talking about the orbits, meaning, what we can think of what happens in orbits could be that you have a picture and you take off and look at the complementary regions. When I look at the complementary regions, that's a difference with Federica's talk. I am recording the data. Like remember, I have these intersection points are part of the data of the components. I'm not looking at the topological components naked. I dress them with these pieces of data. So then, there's more data to reconstruct. Still, notice that yesterday I discussed what we talk about cursors of intersection 1 and 2. If you have more, it's tricky to do that, to do this component thing. So the homeomorphism there, as much as I want to avoid, long words, it's necessary. So you have to think of things that are images by this continuous map. So this is an orbit now. So this was mentioned yesterday, but it's always good to repeat nice results. Mary Mirzakhani, this is a new theorem, and she has a new proof of her old result. Now you can count not only, you have, simple, but, the orbit of a given self-intersection. And again, this is a certain rational, a certain constant that will work for all self-intersections, and this other constant, which is this rational multiple of a power of pi. This is the geometric version of the result that we discussed yesterday, where we saw that orbits look like a rational. This is the inverse of this, rational multiple of pi squared times the length square. So, and in fact, let me just. These two rationals are the same. So the growth, this is, first, when I found it in the computer, I was taking ratios, and so the rationals we found yesterday for the growth, which are, related to how are the combinatorics of the curve in word length, we have this growth. To get the growth that Mirzakhani gets, you have to multiply by this constant. Of course, the results that we're working with Vivek are, the puncture in the torus with one boundary component. We're still in the beginning. Hopefully, we have something interesting to report soon. And we found a proof, kind of, that these rationals, in the case of the torus, they're the same. And here is another interesting thing that happens. So these are the rationals, for the different orbits. And this is, again, for the torus with one boundary component. So for self-intersection 0, that was the special result, there is one orbit. And the reason is like simple curves. If you have a torus with one boundary component, and you have a simple curve, and you remove it, what do you get if you cut it out? Huh? You get an annulus. Well, if you cut it out, there's going to be two boundary components, but there's also a hole. So there's an annulus with a hole. So it's a sphere with three holes. And basically, there's no other thing you can get. So when you have different pieces, when you have one crossing, you have more play of what type of pieces you can get. But as Federica explained yesterday, we can reconstruct the homeomorphism if you have such a simple thing. So here we have, in the case of the torus, we have one orbit. If the surface is more complicated, you have more. And so if I add the rationals, I get, well, there was only one, and there's one orbit. If you add the rationals, in the case of self-intersection 1, there were two orbits. I get 9/4, which is 2.25, and there are two orbits. There are 6 orbits for 2. Well, the approximation of the sum is 5.4. There are 6 orbits, and there are 13 orbits self-intersection 3 that you have to take on trust. This is the sum of the rationals of each of the orbits. And there are 14 orbits. The rationals vary wildly. So this is another theorem that's waiting for young brains to prove it. We need to formulate it in some good way, but okay. Let me not say all this because this is a problem I love. But okay, I'm going to. Gosh. Okay, no, let me just stop here and go to the Goldman bracket so I can give it a little justice. Okay, so let's just go here. Okay, so now, let's start over. I come here, I say good morning. This is on the surface, but it's any curves on surfaces, but it's a change. So let's restart. If you are lost, this is your time to come back. So now we're going to have a surface. It could be with or without boundary. It's oriented, so it's orientable, and it has a fixed orientation. This is the 0 arrow here. And we're going to look at this set of deformation classes of closed curves on that surface, oriented. Now, here I like to emphasize the word set. Some of you know the fundamental group, which is, this classes of base homotopy, and it's a group. This is a set. A group is a set with a structure. This is a set, up to now, no structure. And I'm going to give you a nice structure, meaning there's going to be an algebraic operation satisfying nice identities. So the structure is going to be a Lie algebra, and I'll tell you what it is if you never saw it. So this will be a bilinear map. I'm going to take linear combinations of these deformation classes. These are just formal linear combinations. A curve, the class of a curve and the class of the inverse of that curve, they are not zero. They are just elements, linear combinations, and they're elements in my space. Let me grab this. So if I want to define a bilinear map in these linear combinations, it's enough to pick two elements of the basis and tell you the value of my map in these two elements of the basis, and then you can extend by linearity. So this is what we're going to do. We're going to pick two elements, and we're going to pick one representative of each element. So the blue is one representative of my first element. The light blue is another representative of my second element. I cannot pick any representative. I have to pick representatives that all the intersection points are like this, transversal intersection points. I cannot have points like this, and just for simplicity, I don't want also triple points. You can always, move a little bit your deformation class and make the intersection be nice and clean, like in this picture. And then I look at where they cross. Locally, this looks like a little cross at each point. Now, this bilinear map will have a term for each intersection point. So each intersection point of these two chosen representatives will determine a term. A term is a certain coefficient and a deformation class of curves. So what are these two? So if I look at the green point, the curve that it's going to determine is a curve that starts at the green point, goes around the first element, this is the light blue, comes back, and then goes around the blue element. So this is here, and what I did is I just replaced this little picture here by this little picture here. I did a little surgery, cut out my curve and reattach. Physically you can think, you found two places where you cut your curves. These are now two oriented pieces of curves, and I reattach. Now notice, that I said this is a set. And this thing we did here, it's a loop product. For those of you who saw the fundamental group, you multiply loops that start and end at the same point by going around the first and then going around the other. So when I have loops that I let them wander in the surface, they may not pass, maybe they cross many times, they don't have a special point. But what I do is I said, okay, go to a point where you can perform the loop product and then perform it. And then you get a curve, take a free homotopy class, and then we will add a sign by comparing, since these two are ordered, they determine a certain orientation. So this is, the orientation goes from this to this. And you compare with the orientation of the surface. If it's the same, you put a plus. Otherwise, you put a minus. You do the same with the other point. And and then you have the bracket. So what is the first question one need to ask? Yes?
There's different ways of resolving
Very good. Yes, there is. But my curves are oriented, so I have to follow the arrows. If you and you know those are used too. You can do a bracket with unoriented curves, and then you resolve in both ways. So this is what we did. Now there should be another question. Yes. Yes. Is this well defined? I choose representatives, so it's well defined. Well, of course, the answer is yes, but you know, one should prove it, because when you do things by, you know, doing these choices, you know, you have to make sure these choices don't matter to the final result. So let me emphasize once more. What we do is, you know, we are combining two operations that we know well. You know, one is the intersection. You know, we're intersecting the curves. The other is the loop product. We mix them up, you know, get this beautiful Goldman bracket. So I'll show you in a moment a big idea why is it well defined. It's skew symmetric. You know, this is on the nose because the signs was defined by the order of these curves. And this is the magic thing. It satisfies the Jacobi identity. Well, it's also magic that is well defined, of course. But you know, when you have something like this that satisfies an identity, you have something good. You know, like it's just telling some secret of the surface. So here is a very vague idea of why is it well defined. So say we are computing the bracket of the class of the red with the class of the green. You know, the two greens are clearly in the same deformation class. So you see that here we have this the dark red intersects the red twice, and the green intersected 4 times. And if I compute the bracket, corresponding to this, sorry, let's start with the pink. The bracket corresponding to this point. So I use the dark green representative and the red. And I compute the bracket corresponding to this point. I use the light green representative and the red. It is not hard to convince yourself that you get the same term. It's the same free homotopy class. You can deform one into the other, not too hard. Now, these 3 points, the 3 blue points, they also give the same term. When I say the same term, I say it's the same class and the same sign. Now, there's this one that, you know, here my curve is oriented and goes up, down, up. So the yellow point and the yellow point, which is here, and the blue point will have opposite signs. But again, it's not hard to see that they have the same curve. So when you compute this bracket, well, you get 4 terms because there are 4 intersection points between the red and the light green. But the term corresponding to the yellow is the same as, you know, the same class as the blue with opposite sign. So then they cancel and you get the same thing. Yes?
So I don't entirely get how you choose how to resolve the intersection and how that depends, like, and how you get plus and minus.
Sure.
Would you mind just drawing on that?
I would love to. So you have 2 curves. And let's just put one here. They seem to be all the same curve, but these are the ones that are easy. And here. So suppose I want to find the term corresponding to this point. Now here I have, it's a little bit like a game, you know, where the game says you have to follow the curve, but if you arrive to your preferred point, instead of going straight, you have to turn following the arrows. So I'm this little person, I start wherever I want, here. And I go, tack, 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 tack. Oh, I arrive to the preferred point. So instead of going through the orange curve, I have to turn. And there's an arrow here. This curve is oriented. So the rule is you have to go here. Then I come back here. And then I came back to my point. And when I came back to my point, again, every time you have to go to a point, you have to go here, tack, 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 tack. And then I'm back where I started. So for every term, you're going to have a preferred point that tells you, every time you write here, you turn following the arrows. Another way to say it is like, I'm going to resolve this. So you erase this. And notice that I have arrows. So if I need to complete this, reattach this, following the arrows, I have to. That's the only way, because here, if I want to follow the arrows, that's the only way to do it. Okay?
And then how does the plus and minus go?
How does the plus and minus? So my surface is oriented. Say here we have this orientation. And let's look at this point because this is a little slightly messed up. So here my curve goes like this. When I compute the bracket, this is A, B. So say this is a representative of A, and the yellow, maybe I should. This is the representative of B. So these two curves at this intersection point determine an orientation of the surface, which is look at the forward direction in A and move it to the forward direction in B. So here is my orientation. So this one determines this orientation. So I compare this is the same as this? No. Oh, you get a minus this point. Good. Any other question? I might be going too fast. Murphy? Okay. I'm sure people ask questions. I was just trying to. Good.
Is it okay to ask what the orientation of the surface means? I don't know.
It's totally okay. It's not okay to ask, is it okay? But no, everything is okay. Well, one way to say an orientation of a surface is at each point I have a little arrow like this, like a clock. And then I have to move my clock all around the surface, and the clock can go in the usual clock direction on the opposite. And that's fixed. This is a way. Another way to say it is, well, I don't know exactly where are you, but if you have a tangent plane, you can pick two vectors, and then, there's a way to go from one to the other. It's just, imagine that I draw this arrow and I can move it continuously all in the surface. This is the, you can, that's what we say oriented and orientable. When I have the Möbius band, and this is a nice game to play, if I start and I put in a little orientation here, this clock, and I move it around, I won't be able to. So this is, this is not orientable, and then I cannot put an orientation. So oriented means I can put an orientation nicely in all the surface that is, Very good. Any other question? It's okay to ask. No? Okay. I'm almost at my last minutes. Okay, so let's do a very schematic proof of the Jacobi identity. Oh, by the way, well, I'll say this later, maybe if I have time. So we call it with Janice the stone algebra proof, because these are like little stones that we put together. So I have to compute what is the Jacobi identity. I'll tell you in a sec. It's here. So it means that if you compute the bracket of two elements and you permute them, the three cyclic permutations, you get 0. It's like, so suppose I start to make the bracket of a red and blue class.
Wait.
Yes.
Just so you know, this is a little bit on the exercises, but if you choose whatever you like.
No. Sorry.
Okay.
Out. Yeah, we should have talked this morning. Anyway, I just wanted to say this very quickly before I wanted to talk 2 seconds about a generalization of the Goldman bracket. But we discussed these rings of letters. Seems like centuries ago, but it was Tuesday. Remember that every free homotopy class of curve on a surface is labeled by a ring of letters. These are 2 rings of letters. So now this Lie algebra that we are defining in linear combinations of free homotopy classes of curve, this is a totally abstract Lie algebra in linear combinations of cyclic words. This is, I mean, the ones for you of you who are more algebraic, this is purely algebraic. You can do this without any picture. So, and there's a nice way to have a presentation. This means that if you give me 2 words, my computer, in fact, I have a program in my computer, I can show you, can compute the terms of the bracket, just spit them out. And what is the idea? Well, the idea is I have these 2 words. I want to compute the bracket. Remember that the intersections, well, we saw it with self-intersections, but it's the same with intersection. If I want to intersect this curve and label every point with the pairs of subwords, we have this theorem that tells us that. It's the same idea, there's this thing that, the AA and BB give you this. You have the same if you have 2 curves. You can count intersection of 2 curves by counting pairs of certain subwords. So say these are 2 particular subwords that imply a crossing. Okay, so they look like this. How do you compute the bracket? Well, this.
Are you going to do something like this, like connect them into one color?
Yes. So this tells you, since in the geometry they tell you have to cut them and attach them. Well, here this tells you can cut them in certain spot. The words tell you, you can cut them. They give you a place to cut the words. And these are oriented words, because it's like you have a way of reading them. So when you have 2 oriented things, you can reattach them so that the arrows, make a one single curve. And then the bracket is the sum over linked pairs, these pairs that imply intersection, over some sign that can also be computed combinatorially, and then they cut and paste the curves. Okay, so now, no, let me have 5 minutes. I want to, sorry, this is terrible. Here is one question that upsets me. In fact, this it might even be why I'm here. And I was working on surfaces, and Dennis Oliver, who's now my husband, he wrote, he had discussed about surface, and he said, you might be interested in this Goldman bracket. And I was thinking, well, this is really nice, this bracket, linear combinations of curves, big curves. And, one thing you can do is, you compute the bracket, say this is the output of the bracket. It's a linear combinations of curves. So these A1, A2, AN are, deformation classes of curves. And these are some coefficients. And, this is like a basis, a vector space. You're not going to have here cancellation. These are an honest linear combination. So I can add all these numbers, and how do you think this sum is related to the number of crossings of these 2 classes?
So what are the coefficients? mu1, mu2?
I compute the bracket of A and B, 2 classes. And this is what I get. I get W. So remember, the bracket is a sum over intersection points. You may have cancellation, but can I have more terms than intersection points? No. I mean, maybe you have less. If you start with 2 curves that intersect themselves the smallest possible number of times, maybe there's cancellation. We don't know. So this is a question that, I said, I really like to understand that. And I try to think, is there a cancellation? No. Maybe can the bracket, we do something, and can they tell us whether a curve is simple or not, if the bracket is something? And, we started talking, and there was this nice conjecture that I can tell you, but I don't have time. And then we had this nice conjecture that we tried to prove. I came here to the States, I started working with him, I started dating simultaneously. It was quite complicated. In fact, I always said, some women, when they started dating, they get chocolates and flowers. Well, I got the Goldman bracket. And we tried, and in the midst of that, we find this other interesting, because we were studying, the forming curves and families of curves, and homotopics of curves, and we managed to generalize this bracket to higher dimensions. Never proved that conjecture, which later on, using this program and this combinatorial description of the Lie algebra, I found the counterexample. So I have half a minute. I wanted just to show a tiny bit of this structure that we found. I was much more hopeful this morning, which is the following. So suppose you now, this is again half overview of what may happen, something that will Natalie will talk about next week. So we're looking at a new, bigger, much bigger, my higher dimensional space, the space of all map from a circle to a manifold. You can think of a 3 manifold, a 3 sphere, or it could be in a surface. This works for any dimension. So this is, we think of this. This is the loop space, and we're going to take the components on this space. This is a space, and with a natural topology, we take the component, and we're going to consider linear combinations of these components of this space of maps. So this is the H0 of the space. If you know something, this is equivalent homology, but let me not talk about this. Now, let's look at one family of map from the circle to the manifold. So one family of map, you can think of, here I have one family of circles outside. The circles are, this arranged in a torus. It's a continuous one family. That's why I can arrange it in a torus. And then I'm going to map it to the manifold. So you can imagine your torus there, but the structure, remembering that here I have the circles is there. Okay, I know, I'm out of time. So now I'm going to tell you how to define a bracket between two elements like this. And it's just, the usual joke with mathematicians that we reduce to the above procedure. You repeat what you know how to do. So you have this object, which is a map from the torus to the manifold, and the other object, which is a map of a circle or a class. And you're going to look at in your 3 manifolds. Since I have a 2-dimensional thing and a 1-dimensional thing, they may intersect in points. If I put a nice, if I put my transversal earrings, you can come and look at them later. This is transversality. Now, when they intersect, remember that this torus is made of circles, like tuck, 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 tuck. So at each point of the circle, I can make the little surgery I did for the bracket. And that's a linear combination. So the torus and the circle will give me a linear combinations of curves. And I'm going to do the last, I know, I'm so sorry. And when we have 2 torus, you can do the same. A torus and a torus, now they're going to intersect in circles, They intersect because there are two-dimensional things. They intersect in a 1-dimensional thing, but they're nice and close. So at each point of the intersection, there's one circle of one torus, and there's another circle of the other torus. So at each point, I can go run one loop of one torus and one loop of the other torus. This gives me one family of loops at each intersection that is parametrized by the grand circle. So this is a generalization of that bracket. Say too fast, I know, and I'm done.